Okay, start.
So, good evening, sir. We are the Group 5. So, course, MTEC 101, period finals, week 2, session 1, and the topic is the sextant altitude of sun and moon. So, next slide. So, course outcome. Solve problems by getting the altitude of the sun and moon. So, learning outcome. At the end of the session, the students shall be able to determine the sextant altitude of the moon and sun. So, the importance of the topic. So, getting the altitude of the heavenly bodies such as the moon and sun to get the position of the own ship in the sea. So, sextant altitude by moon and sun. So to start, what is sextant altitude? So, it is the angular height of an object above the visible horizon or as a read from the arc of a sextant before correction for index error if any. Observed altitude. This is the angular height of an object above the visible horizon as read from the arc of the sextant and correction for its index error. So sextant is an essential tool for celestial navigation and is used to measure the angle between the horizon and a visible object or two objects at sea. By the help of sextant mariners are able to get the altitude of the heavenly bodies using this instrument known as the marine sextant. So with the most common heavenly body known as the sun and moon, these heavenly bodies are the most common target for getting altitude. In the ship, sextant altitude is the angle subtended at the observer between the visible horizon and the object. By the night time, to get on ship position in the earth, moon and sun are available target, while during daytime, sun is the most common heavenly bodies to make us target for getting altitude. So, to continue please, Fernandez, J.
Uh, Good morning, sir. I'm Fernandez JP. Sextant altitude by moon and sun. Why is it important for mariners to get altitude of the two heavenly bodies? In the early days of navigation at sea, mariners traveled along coastline and always stayed in sight of land. Sailors compared the distance between landmarks on the shore to gauge their progress at sea and estimate their geographic position. Using recognition and landmark, fishermen could find their way back to good fishing grounds and traders could steer to distant ports. However, using this visual navigation technique restricted sea travel to shorelines could be challenging on foggy days or when visibility was poor. Sailors could only venture out into open waters when they could follow in wide continental shelf or rely on predictable ocean currents and winds. In time, mariners developed new methods of navigation for traversing open waters in many different regions of the world. Navigators created surprisingly accurate navigation technique based on the sun, stars, and other elements of their environment. Next page. Sextant altitude by moon and sun. Watching the sun in daylight, one of the simplest methods for determining a shape direction was to watch the movement of the sun across the sky. Sailors used the position of the sun as it moved from east to west to guide their route. At noon. They could determine north and south by the shadows of the sun. Next page. Sextant algebra by moon and sun. When the sun set at night, sailors used the moon and stars to navigate. The moon moved across the sky from east to west, and some stars, called rise and set stars, begin and end their nightly path below the horizon, sailors determined their heading by watching the movement of the moon and stars at the same way they watch the sun's movement. Sailors measured the height of the moon in the sky to track their progress. Sailors also used their knowledge of the constellation to navigate because constellation changed seasonally. Mariners had to know which constellation were visible in the sky at different times of the year in each hemisphere based on the location of certainly constellation in the sky. Sailors could determine what direction they were heading. Next page. The North Star was also a valuable marker for early navigators. When the sun set at night, sailors used the stars to navigate. Stars move across the sky from east to west, and some stars called rise and set stars begin and end their nightly path below the horizon. Sailors determine their heading by watching the movement the way they watch the sun's movement. Sailors measured the height of the stars in the sky to track their progress. Sailors also used their knowledge of the constellations to navigate. Because constellations change seasonally, mariners had to know which constellations were visible in the sky at different times of the year, each hemisphere based on the location of certain constellations in the sky. Sailors could determine what direction they were heading. The North Star was also a valuable marker for early navigators. Next page. This is the example on how to get the altitude of the sun. Example, date equals May 20. Apparent altitude of the sun's lower limb 10 degrees 47 minutes. Ang correction equals 11 minutes point 1. Interpolating as necessary. The next reporter is Kurt Hinayon.
Full example of altitude corrections for the sun. The following examples show how altitude corrections for index error, dip, semi-diameter refraction, and parallax are applied to a sextant altitude of the sun. So on 12th of February, a reading of a sun's lower limb was taken. So the sextant altitude from observed target is 14 degrees 35 minutes, point 5 35.5 minutes. So index error is negative 2 minutes point 3 and height of eye is 4.2 meters. Temperature during the time is 20 degrees Celsius. Pressure is 1002 MB. Using the extracts of tables A2 above A4 below, the calculations for the true altitude would be as follows. Next slide, please. So here, as you can see, is the nautical almanac. So sextant altitude 14 degrees 35.5 minutes. IE is negative 2 minutes point 3. Observed altitude 14 degrees 33 minutes 33.2 minutes. Dip is negative 3.6 minutes. Apparent altitude is 14 degrees 29.6 minutes, and the sun's correction is from the observed nautical almanac is plus 12 minutes, 12.6 minutes combined correction. So now the result would be, or the true altitude is 14 degrees 42.2 minutes. Next slide. Here, example on how to get the altitude of the moon. So example at 0200 GMT on 24 December, the sextant altitude of the moon's upper limb is measured on the following data. Sextant altitude from observed from the moon is 33 degrees 15 minutes, and the IE is equals to 1.8 minutes. HOE or height of eye is 18 feet. So HP is 54 minute 0.9 minutes. Using the extracts above, the true altitude is calculated as follows. Next slide. So here in the nautical almanac, it's not just very clear, but sextant altitude is 33 degrees 15 minutes. The IE is, or the correction is the plus 1.8 minutes. The observed altitude is 33 degrees 16.8 minutes. Deep is negative 4.1 minutes. The apparent altitude is 33 degrees 12.7 minutes. And the correction for apparent altitude is plus 57.4 minutes. So for HP, upper limb is plus 2.1 minutes. And then the result would be 34 degrees 12.2 minutes minus 30 minutes 0.0 for upper limb. The true altitude now is 33 degrees 42.2 minutes. Next slide. So here are the references of our report. That would be all.